Welcome to this NPTEL course on Advanced Pre-stress Concrete Design. We are moving into the new module, module 7.1 on continuous beams. This will be the part 1 and then we will have one more part which will talk about concordant cable profile and so on. Okay, what are the expected learning outcomes? After the student undergoes this video, he or she should be able to understand the advantages and disadvantages of going for continuous systems in general, and then analysis procedure for considering the effect of secondary moments due to the pre-stressing in a continuous system. How do we find the secondary moment? How do we find the total moment including the secondary moments? We will examine through an example problem. And the student should be also able to gain knowledge on the effects of both secondary and tertiary moments in a continuous system. So, in addition to secondary moments, there are also tertiary moments that are possible. That also we will discuss it in the later part of the course. Okay. Now, continuous beams are very prevalent in the modern day construction. For example, in a typical building frame like this, we can have a continuous frame. For example, if it is done in a cast in place type of construction, post tension system, post tension beams are quite common, especially when you have huge load and long spans. Post tensioning girder is a very good method of designing an effective structural system. This is the way that you have it in a building frame. Typically, you have cables that will be run in this way, right. So, you have a cable like this and goes into support, goes like this and then goes up, and then it will be fixed like this, right. Similarly, you can also have in a bridge system, the deck can be, or the superstructure can be made continuous system. Every 3 or 4 spans you will have an expansion joint. So, and then you can design. So, with continuous system we can design a more effective and economical design. So, that is what the advantage of a continuous systems. Now, let us look at in detail what are the advantages and disadvantages of a continuous pre-stress concrete beam. Okay. So, you see here in a continuous pre-stress concrete beam, we have a straight tendon like this. So, if what is that it is going to happen here is you have a tendon with, let us say, a constant eccentricity is there, right. Now, if I am doing the pre-stressing, let us say that this is a post tension beam and I have a constant tendon profile with an eccentricity of E. When I do the pre-stress, if that intermediate support B, you assume that if it is not existing, then what will happen? Because of the pre-stress, the beam will try to lift up, right, and it will try to lift up by, let us say, a deformation or a displacement delta. Now that I have the support will try to pull the beam down and make the deflection to be 0. So, that is what the support is. Because you have support, the beam cannot deflect upward due to the pre-stressing. So, because I have to prevent this deformation, there is a reaction that will be developed which is going to push the beam downward, that we need to evaluate what is the effect of it. Now, because of this reaction, we know that, let us say, the span is L here and L here, that the total span is 2L. Let us assume that if this reaction is applied like an external load, you will find that the secondary moment due to the reaction will be, typically for concentrated load we take WL by 4. In this case, W is R and L is 2L by 4. So, you get moment equal to RL by 2. That is what we have here. So, this is a secondary moment. So, this is a moment that is developed by the virtue of the system being continuous, and a reaction will be developed when you do the pre-stress to keep the beam at the support level and you are preventing that uplift. So, that is why the secondary moment profile typically will be a linear profile. Okay, now let us look at what are the advantages and disadvantages of continuous system. And now, as you can see from here, usually continuous system will have higher load capacity for the same span and section dimension, and mid-span deflections will be less. The depth at a section can be less than for a simply supported beam. That you know why we have, because continuous system can take alternate load path and the stiffness is also going to be higher. So, your deflections requirement and your resistance moment what you are developing is also going to be lesser. So, the continuous beam results in a more economical design. And also there is a redundancy in the load path. That means that we can generate alternate load paths. So, you can form actually hinges in case of an extreme event. For example, in the case of an earthquake, I can form hinges at different locations that can help me to develop alternate load path. And in post tension system, now I can run a cable from one end of the beam to another end. So, if I am able to go for a continuous system, typically we do not need more anchorages. So, it requires less number of anchorages. Instead of doing, let us say 3 span continuous system, you do 3 simple spans, then each span we need more anchorages, right. So, 2 anchorages at least, right. So, but here in a continuous system you need anchorages only at the 2 ends, right. So, continuous system will actually lead to less number of anchorages. And now, when you go for continuous system, particularly in bridges, the number of deck joints and the bearings can be reduced. So, the moment you can cut down the number of bearings, the maintenance required will come down. So, these are all the advantages of continuous system. Of course, it is economy and it can take more load, there is a lot of alternate load path and the requirement of anchorages are going to be high. All these things are advantages. Now, there are also some disadvantages. So, let us look at that. The one is, of course, you have continuous systems are statically indeterminate depending upon the number of supports and the degree of continuity. Then your analysis and design procedures will become somewhat difficult than simple spans. And it is also difficult in terms of construction, especially when you are using precast systems. If you are going cast in place, you can run the duct and then you can stress it from one end to another end. But if you are combining precast and cast in place for a continuous system, then difficulties in construction increases. And another disadvantage is, because I am going to have, let us say particularly this is valid for a girder, where you need to change the curvature profile of the tendon for a large number of spans, your friction losses will be high due to the change in the curvature of your tendon profile. Now, you can also have increased shortening of a beam leading to lateral force on the supporting column. This also we will see that this is called tertiary moment will be developed because of the shortening effect on the beam, because of the shortening when you do apply the pre-stress, the beam undergoes shortening. But however, because if the beam is connected to the column will also prevent that shortening. So, in that case there will be some lateral force and moments will be developed on the supporting column. So, we need to account for that. Now, secondary stresses also develop due to time dependent defects like creep and shrinkage, which is again first of all, the creep and shrinkage itself, accurately calculate their effects itself is not possible, and settlement of support depending upon the support condition that you have, then again that also it is a highly nonlinear process. It depends upon site condition and it varies with respect to time. So, all these things lead to more secondary stresses which are very difficult to estimate accurately. These are all some of the disadvantages of going for a continuous system. Having said that, advantages are much higher than some disadvantages. So, in the modern day construction, continuous systems are becoming more and more common. Okay, what are the cable layouts that we can consider for continuous systems? Okay, we can also combine the precast systems and cast in place construction to come up with continuous system. Let us look at some typical cases. For example, this you have a system, a simple 2-span girder and I can run a cable like this. Of course, the cable, you know that it should ideally follow the bending moment profile. So, that is why we put the cable profile like this. This is a continuous cable. The second one can be the CG of the concrete can be varied. So, here if you look at it, this is your CG of concrete and this is your CG of the steel. Now, you see here the distance between the CG of the concrete and CG of the steel is what creating that primary moment. So, here in this next example, you see here CGS is pretty much constant, right. However, the CG of the concrete element, basically it is going to change depending upon the cross section. It is going to follow the profile of the beam itself, somewhat like this, right. So, this is going to be somewhat like CGC. So, you always going to have eccentricity. So, this is another way of doing, keeping the cable straight, but varying the concrete section depending upon the expected bending moment that you are going to get. The next option is combining. So, this can be now made precast. This can be made precast. Now, I can combine them through a cap cable. So, you see this is a cable that will be done after putting the precast system and you will be stressing it from the bottom. Okay. So, you should have provision for jacking and stressing from the bottom of this location. So, in this way the cable will be at the top location with the support, that is where you are going to develop some hogging moment and the cable should be at the top location. So, this is another way of combining precast and this will be a cast in place concrete. Okay. So, we are combining precast and cast in place concrete. The next option is there, you can have again precast, this is also precast and you do the post tensioning, then you provide a slot. In the slot what you do is you attach this straight cable to take care of the hogging moment. So, you need to have provisions for attaching the jack and then do the tensioning and so on. It is more involved, you have to plan for it. Then you can go ahead and fill this joint. So, the joint can be filled later condition. Okay. So, this way we can again achieve continuity using precasting and cast in place concrete. Okay. So, this is another example of splicing the precast girder. So, you can see here that this is one girder, this is one girder. They can be spliced by having some couplers as well. Okay. So, couplers are directly you can attach it and add additional cables, okay, and then you can pour that region where you are adding some extra cable to create that continuity. So, in this way also I can create continuity. This is the splicing of precast girder. Splicing, as you know, is very common in steel structures, but if you plan it well, that can be done in your precast concrete construction as well. Okay. The next point is pressure or thrust line. Now, for a statically determinate system, you know that while you do transfer the pre-stress, you do not develop any secondary moment because they are statically determinate. So, the location of your pressure line will coincide with that of the CG of the strand, right. So, there is no change, but in case of a continuous system, while you transfer the pre-stress, because you develop secondary moment, there will be a shift in your pressure line or your thrust line, which we need to account for it. So, let us see this example. For example, again you have a 2-span continuous system with pre-stressing cable at a constant eccentricity E. Now, what would be the primary moment that will be developed? It will be minus P into E. Now, why I am taking this minus is pre-stressing has to oppose external loads, right. So, that is why typically the E, if it is below the CGC, it is considered positive, the eccentricity. So, the positive eccentricity will create a negative primary moment. So, that is why we are saying this as a negative primary moment, which is P constant throughout the both the spans. Now, we have seen in the previous example that there will be a reaction that will be developed that is going to push the beam downward like this, right. That reaction will create this positive bending moment like this, okay, which I am calling this as a plus MB. Of course, you have to find this reaction R, and then you have to, if you find the reaction, then you can quickly calculate what your plus MB is. Basically, nothing but R into 2L by 4. And the variation of secondary moment is always linear, because the secondary moments are produced only by the reaction that are developed at the supports, which are point loads, right. So, you are going to have bending moment profile is going to be linear. Now, when you add both of these things, you see here pre-stressing is going to create negative moment here and a positive moment at the support and a negative moment here. So, which is what we want. In the span locations, pre-stressing should create a negative moment. At support locations, you need to create a positive moment. So, this is the resultant moment. So, you have to account for this. Okay. So, now you see, now this is the resultant moment. Now, what is the pressure line? Pressure line is always denoted as EC, the location of your compression force. So, that is coming from the resultant bending moment Rm divided by the pre-stressing force P, right. So, the resultant bending moment, for example, if you look at this location, it is going to be Mb by P minus E, because I am dividing Mb by P and Pe by P. So, Pp will get cancelled. So, at this location you will have EC, this is your eccentricity of your compression force. So, this is your EC, okay. So, this is your EC. Okay, this is the location of your thrust line or your EC. Okay, so this is your EC. So, the location here EC, which is a thrust line. Okay, small e we denote it for eccentricity of the tendon. When you say EC, it is the eccentricity of the compression force, right. So, or nothing but it is the location of your thrust line along the length of your beam. Okay. Okay. Now, what are the steps involved in analysis? Okay. In the step 1, first we need to get envelope moment diagram. So, why should we get envelope moment diagram in a continuous system? How do we get it? Because we have to consider pattern loading. Okay. So, we need to create the loading patterns and do the analysis in such a way that I will get positive moment for midspan as well as negative moment, maximum negative moment for support location. So, how do we get that? First, we need to do the analysis by considering live load in all the spans. Then you get your one bending moment distribution. Then what we do? Especially when you want to calculate what would be the maximum support moment, typically what we do is we consider the dead load on all the spans, but live load will be considered only in the adjacent spans of the support for which you are trying to calculate the maximum moment. Okay. Usually, the effect of load in the alternate spans beyond is neglected. For example, I have a multiple supports like this. If I am trying to calculate only at this location, let us say A, B, C and D, then I load only this and this span, but I do not load, this is basically a live load, right. This is for moment at MB, negative moment MB, right, support moment MB. So, this is how we load it, and then we consider your moment profile. Then what we do is for span moment, now let us say for example, I want to calculate the span moment at midspan of PC. Then I put live load in the span where it is considered and the alternate spans. So, for example, let us say here you do not consider that, let us say I have it here, let us say this is E. So, then if I want it in this midspan of BC, then I leave these other two and then alternate span I put live load. Of course, dead loads have to be considered in all the spans, right. So, for span moment we consider the live load only in the span where we want and in the alternate spans. So, like this we do multiple analysis and then we develop this locations where we will develop this negative moment or minimum moment or positive maximum moment. So, this is an envelope diagram for considering the effects of different locations of live load positions for getting the maximum span moment and the maximum support moment. And this is from external load. So, the M0 envelope diagram comes from your external loads, right. Okay. Now, we said for a statically determinate structure, when you apply pre-stress, you not only generate pre-stressing or primary moment, you also generate secondary moment. Let us first calculate step by step what is the primary moment and what is the secondary moment. Now, M1 is a moment from pre-stressing. So, let us say this is an M1 diagram. So, this is the moment diagram due to the eccentricity of the pre-stressing force from the CG of the concrete, and we do not consider the effect of your intermediate supports when you calculate your primary bending moment. So, that means whatever the profile that you have, that will be the profile of your pre-stressing moment as well, P into E, right. So, now we can ask, of course, the pre-stressing force, especially in a post-tension system, it can vary along the length of the span if you consider the losses, right. But if you neglect the variation of your pre-stressing force due to frictional losses, the value of M1, which is a primary moment, will be proportional to E. Hence, the shape of M1 diagram will be similar to the cable profile. So, this is nothing but just the pre-stressing force multiplied by the eccentricity of the cable. So, that is your M1 diagram. This is also called as primary moment diagram. Okay, this is a primary moment diagram. Okay. Now, how do we get your secondary moments? Again, we take this simple two span system, and if you just look at, because of this cable profile, we look at what is the equivalent. So, these are the equivalent loads from pre-stressing. If I look at only free body diagram of the concrete, we can see that let us say each span is loaded with W, right. Then I can find out that W also we can find out from each span like this. How do we get that? We know that WL square by 8 for each span is basically P into E. From each span, then I can get my W. If eccentricity is same, then for each span W will be same. So, we can find that, right. And then we apply this load. Now, simplified free body diagram. So, what we are saying here is, you are going to calculate the moment due to the load from pre-stressing, ignoring the intermediate support. So, that means what? Assume that this support is not existing, though it is there, and then you calculate what is the primary bending moment. So, for example, this is the entire span. Now, this is L and this is L, and assume that this is not existing. Okay. So, what would be that? So, basically, now I have a load W acting over a span of 2L. So, what will be the maximum moment? W L square by 8. So, it is going to be 2L square by 8, which is going to be W L square by 2. So, that is what we have. And so, if I have to measure P equal to W L square by 8, then W L square by 2 can be written as minus 4 into P, right. Now, what is secondary moment? Secondary moment, let us say that we that secondary moment, I have to find or calculate the secondary moment. First, I need to find this reaction value. Now, how do I find this reaction value? You can either use the principle of superposition, for especially for a two span structure, easily you can calculate your delta. As we have seen, for a two span system, let us say that you are going to have a beam that is going to lift up like this due to pre-stress, right, and this delta is what we are going to have, and this is one system, right. Now, the another system, what we are saying is the reaction should be applied in such a way that, right, this is going to create a net, delta U and let us say delta Okay, so you say here, no, I am going to keep like this. Okay, downward deflection. This is because of the reaction that is on. So let's say this is delta down, delta D. So delta D. So you can see that delta U should be equal to delta D. Then I can find out the reaction R in a very simple way, right? So this is what method of principle of superposition, using method of superposition. I can calculate this. So for example, this is your loading will be like this due to assume that support is not existing. So we can calculate what is this W, okay, due to pre-stressing, and then you find out what is the delta U it is creating. Now there should be an R in the middle support so that the deflection will be nullified. So you can calculate your R from this. So for simple two-span system, I can use this method of superposition and I can calculate my R in a very simple way. But for if you have more number of spans, then either you have to use flexibility approach or we may have to resort to moment distribution method to calculate your moment that is coming from your pre-stressing. So that we will see. So the whole point is, let's say that we have found R like this. If I do that, then R I can, for this example, I can estimate that as 10 WL by 8. Okay. So that we got that. Now what would be the moment that will be produced by this 10 WL by 8? We can see this into L by 4. If you put it, you will get that moment as 5 WL square by 8, which is equal to 5 into P, assuming P is equal to this WL square by 8. So these are all some simplification. Now what is the point to note here is, the secondary moment will be developed because of the reaction that is coming at the intermediate support. So due to pre-stress, I have to consider both the primary moment and the secondary moment. So the net final moment due to pre-stressing is going to be this. So I am going to have some positive moment at the support, some negative moment here. Okay, I need to superposition M1 plus M2. So in other words, M2 can be written as M1 plus M1 prime. M1 is a primary moment diagram and M1 prime is the secondary moment diagram, including the effect of your reaction that is developed, and that is going to create some additional moment, secondary moments, which need to be considered. So M2 is the moment that is coming from secondary moment. Now for statically determinate system, for M1 prime is going to be 0 for statically determinate system. Because this is simply supported beam, when we do the pre-stress, it's free to lift up, there is no support in between to hold it down, right. So that is why we never develop M1 prime in a statically determinate system. M1 prime will come only when you have indeterminacy or a continuity in the pre-stressing beam. Okay. Now let's see how to do the analysis, okay, structural analysis. Finally, our goal is to find out the exact distribution of bending moment due to pre-stressing, and then we get your envelope diagram because of your external load that, let's say, that you get from your structural analysis. We sum them up and then the net moment we actually design for it. So our goal is, now in this continuous system, I want to find out what would be the net bending moment distribution considering both the primary moment and secondary moment. Let's see how do we do that. Okay. So for a general case, the resultant bending moment at any location, as we have seen, due to pre-stressing, again this is due to pre-stressing as we explained, M1 plus M1 prime, right. Now what is M1? M1 is a moment again due to the eccentricity of pre-stressing neglecting the intermediate support. That means it is going to be pre-stressing force multiplied by the eccentricity, and M1 prime, this is M1 prime, right, moment due to the reactions at the intermediate supports, and P is effective pre-stressing force. When you say effective pre-stressing force, basically you are considering, well, M1 is the primary moment and M1 prime is the secondary moment. What is the total moment? Total moment, as we have seen, this M0 we have considered from the external load. This is the moment envelope. Moment envelope. that is coming from external loads, right. So, M3 is the final moment that we need for design, which will be summation of M2 plus M0. Now, what is M2? M2 is summation of your primary moment and the secondary moment. So, totally we can write M3 as M1 plus M1 prime plus M0, where M0 is your moment envelope from external loads. Okay. Now, what are the important characteristics of all these moment diagrams is, as we said, always pre-stressing should be designed, pre-stressing moment should be opposite to external moment. Okay, that is the design. So, we want to nullify that external moment as much as possible, right. So, the pre-stressing moment always should oppose the external moment. That is the reason what we say is a positive eccentricity of the CGS will create a negative moment. Okay. When will you have positive eccentricity for a span like this? Let us say for a section like this, and I have, let us say, just strand is like this, right. So, I consider this eccentricity. When it is below CGS, CGC, then we consider this as positive. So, that is the reason you see here, when the eccentricity is below the CGC, that is going to create a negative moment that will be offsetting the positive moment that is coming from your external load in the midspan, right. So, it is going to create an upward thrust. Now, M2 diagram, okay, typically it is positive, has a similar shape as that of M1 diagram, which is again similar, right, to the profile of the CGS. Okay. So, why is it so? M2 diagram will have same profile as that of M1, because M1 prime is always linear. So, when you have a parabolic moment profile and you add a linear profile, you will finally end up with a parabolic profile. So, that is the reason. The secondary moment diagram will always be linear between the supports. So, when you add that, so M2 will actually going to follow the profile of M1 diagram, right. So, these are the things. So, the final goal is, you have to put sign conventions in such a way that the pre-stressing is going to be, or we design it in a way that pre-stressing is going to oppose the external moment that are developed. So, that is you have to keep it in mind.